Welcome to the mysteries of the cosmos. The cosmic microwave background radiation is one of the most important discoveries in the history of cosmology. This faint light that fills the entire universe is the remnant echo of the Big Bang, offering us a direct view of the primordial cosmos. Discovered accidentally in 1965 by Arno Penzias and Robert Wilson, it revolutionized our understanding of the universe. It originated approximately 380,000 years after the Big Bang, when the universe cooled enough for the first atoms to form. Before this moment, the universe was a hot, opaque plasma where light could not travel freely. As the universe expanded and cooled, electrons combined with protons to form neutral hydrogen atoms. This process, known as recombination, allowed light to travel freely for the first time, creating the cosmic microwave background radiation. Since then, this radiation has traveled through space and time, cooling as the universe expanded. Today, we observe this radiation as a faint microwave glow that uniformly fills the entire sky. The temperature of the cosmic background radiation is incredibly uniform, with an average value of 2.7 degrees Kelvin. This uniformity is key evidence for the Big Bang theory and cosmic inflation. However, detailed observations have revealed small fluctuations in the temperature of the cosmic background radiation. These fluctuations, on the order of 1 part in 100,000, are crucial to understanding the formation of structures in the universe. Slightly denser regions in the early universe became the seeds of the galaxies and clusters we see today. The study of these fluctuations provides us with invaluable information about the composition and geometry of the universe. Patterns in the cosmic microwave background radiation allow us to measure the amount of ordinary matter, and dark energy in the cosmos. Furthermore, the shape and size of these fluctuations tell us that the universe is remarkably flat in its overall geometry. The cosmic background radiation also provides us with evidence of the age of the universe, estimated at about 13.5 billion years. To study the cosmic background radiation accurately, scientists have launched several satellites and made observations from Earth. Missions such as COBE, WMAP, and Planck have provided increasingly detailed maps of this primordial radiation. These maps are like a snapshot of the universe when it was only 380,000 years old, a fraction of its current age. Analysis of the cosmic background radiation has also allowed several cosmological theories to be tested. For example, searching for specific patterns in the polarization of this radiation could provide direct evidence for cosmic inflation. The cosmic background radiation also helps us understand the thermal history of the universe and how the first elements were formed. In addition to electromagnetic radiation, scientists are searching for an even older cosmic neutrino background radiation. The study of cosmic microwave background radiation also has implications for the search for primordial gravitational waves. These waves, predicted by inflation theory, would leave a characteristic imprint on the polarization of the cosmic background radiation. The cosmic microwave background radiation also helps us understand the large-scale distribution of matter in the universe. The structures we see today, such as filaments and cosmic voids, have their origin in the primordial fluctuations visible in this radiation. The study of the cosmic microwave background has led to the development of what is known as the standard cosmological model. This model describes a universe that began with the Big Bang, experienced a period of inflation, and then evolved to its present state. Despite its success, the standard cosmological model still faces challenges and unanswered questions. For example, the exact nature of dark matter and dark energy, which together make up 95% of the universe, remains a mystery. The cosmic background radiation also poses its own puzzles, such as certain large-scale anomalies that are not easily explained by current models. As our observational techniques improve, we may discover new details in the cosmic microwave background radiation. Future experiments could reveal signs of physics beyond the standard model or evidence of phenomena such as cosmic strings or bubble universes. The cosmic background radiation also provides us with a natural cosmic clock, allowing us to measure the rate of expansion of the universe over time. This cosmic clock is crucial to understanding the history and fate of the universe, including the role of dark energy. The study of cosmic microwave background radiation also has implications for particle physics and the search for new physics. Ultimately, the cosmic background radiation is a testament to the unity and shared history of our universe. It reminds us that, despite the vast distances that separate us, we are all part of a common cosmic narrative that began almost 14 billion years ago. Thank you for joining us on this stellar journey. If you liked this cosmic journey, don't forget to give the video a like. Subscribe to Mysteries of the Cosmos for more space adventures. See you in the next video.